Hi, in this video I want to show you how we can derive or create one final kinematics equation so that we can measure motion. Kinematics is the branch of physics where we try to just measure the motion of an object without explaining why it's moving. And in this final equation, we get it from graphs. I want to show you this velocity time graph here of an object that is moving at 3 meters per second for 7 seconds. Using this graph, we're able to figure out the displacement of this object. If you remember, the displacement of an object can be found by taking the average velocity multiplied by the time. But I want you to notice that we also can visualize the displacement of this object if we consider this to be a rectangle and find the area of this rectangle, the area underneath this line. So the area underneath this line, I'll shade it in here, is going to equal the length times the width of this shape. The length right here is the time. That's 7 seconds, right? So that's a time of 7 seconds right here. And then the height of this rectangle, or the width, is just going to be this velocity that it's traveling at, and it's going at a constant velocity, so the average velocity is just equal to the constant velocity here. And so to find the area of this rectangle, we take the length times width, that's velocity, times the time. And so what we discover is that the area under a line like this is equal to the displacement of the object, or it is the displacement of the object. Okay, that's nothing breakthrough, nothing remarkable there, but when we have an object that's accelerating, we get a new equation out of this. And to show you that, I'll show you how we can do this. We want to find the area underneath this line again. So to find the area under this line, we are going to split it up into two separate shapes. So I'm going to make a rectangle like before, and I'm going to make make sure I draw this correctly, a triangle here. So splitting it into two shapes allows us to more easily find the area. So the displacement of this object is going to equal the area of the rectangle, I'll call it area 1, plus the area of the triangle, which I'll call area 2. So let me shade in my areas now. I'll shade in the triangle area just to visualize it here, and shade in my rectangle again. Now this time we're not going to be dealing with the average velocity, but the initial and final velocities, or the change in velocity. To find the area of this rectangle, we're going to have length times width again. So the length of this rectangle is equal to the time that goes by. So I'll put that right here. Time multiplied by this width right here, which, if we're thinking about what's happening here, this object is speeding up and it starts out at 3 and it ends up at 8. This is the starting velocity, so we could call that the initial velocity right here. So we would say the initial velocity multiplied by time for area 1. Okay, but we need area 2 as well, so how could we label this? Area 2 is going to be equal to the area of a triangle. And the area of a triangle is 1/2 base times height. So the base of this triangle is going to be the time. So I will write 1/2, and then the base, which we said was time, multiplied by the height of this triangle, which is going to be equal to this portion of our graph here. It goes from 3 to 8. And this is going to be equal, this increase in our velocity is also known as just the change in velocity right here. So we'll call that delta V. And so I'll put in right here in parentheses the change in velocity for area 2. So we have 1/2 t times the change in velocity. If you recall from a previous equation, the acceleration of an object is equal to the change in velocity over time. So I could rearrange that equation, multiply by time on both sides, and we get the change in velocity is equal to the acceleration times the time. So I do that, and instead of writing, the change in velocity here, if I substitute in this acceleration times the time, I get 1/2 times time times the acceleration times time. And I'll add that to my initial velocity over here. And this is my equation for displacement. Now I can simplify it one more step here by multiplying these two times together to get time squared. And so I will write down the full general equation here, that the displacement of any object that's accelerating will be the initial velocity times the time plus 1/2 acceleration times time squared. So this is the displacement for any object that is accelerating. And so now we have the final piece of the puzzle. We now have 5 major equations that allow us to calculate basically anything we want in kinematics. So we have 2 equations for average velocity, 1 variation right here. I've written the variations in blue. We have the acceleration equation, which is a key equation to all of this, with some variations of that equation. And then 2 more equations that we've kind of put together from our pre-existing equations. One for final velocity squared, and one for displacement. So these are the kinematics equations, and they have a lot of applications. We'll look at some example problems in a future video. So that's all I've got for you in this video. Remember, everything you have is a gift.